So once again, if you're in the room, you can ignore me. So if anyone watches this class recording from today, which might be a couple people, I was gone the first 10 minutes and I showed a video with the really long name. It's molality, molarity, and mole fraction from percentage. I will put that link to that video on the daily plan. So watch that video first, and then right now in class, we're trying to do this where I've changed the numbers, and we'll work through that together. So please go back once again and watch molality, molarity, and mole fraction from percentage. Hold on. So for mole fraction, there are no units, and it's not a percentage. I know I just said that, but I was repeating that for the video. All right. How many of you need me to work through how we got that?
No.
Okay, well, that's a miracle. Maybe I should start with the 5-minute video every day.
Yeah, Fabian presses play.
There you go. I'll take a 10-minute longer lunch every day. I like this idea. All right, then molality. When you came up here, we don't have to work through it, but help me out. How many moles of HCl did we have here?
11.9.
11.9. All right, and then moles of H2O?
36.3.
36.3 or 4?
3. Is it 3 repeating? Yeah.
Okay. So molality, I'll need the moles of HCl, which is 11.9. All right, and from up here, you had to find the kilograms of the water, correct? To find this value. So what was that number?
For the solvent, that'd be 654.
All right, so 654 grams. Everyone agree?
Yeah.
Which is really 654 kilograms. And so that equaled
18.2.
18.2. Okay. And molality, the unit can be a small m, but usually it's just MOLAL, molal. If you put a little m, you'll be fine. You'll get it right. Yeah, Judah.
I'm still having trouble covering kilograms.
From the grams, you just move it 3 to the left. The 654 came from 60% of the mass of this substance was H2O. We used the density of 109. We multiplied that by 1,000 because that's how many milliliters there are in a liter. So we got 1090. That's ugly, times 0.6, and that's where we get 654 grams. That's where we divided by 18 and got 36.3. Well, don't do that again, Judah. All right. So that's where that came from. We moved it over 3. All right, molarity, since we decided to do this with 1,000 milliliters or 1 liter, it was pretty easy. We ended up with 11.9, right?
Yeah.
So you basically just find the moles in the beginning of the process.
Right.
Well, the moles
Because
are given to you by trying to solve for the fraction.
Right, by assuming we have a liter of the solution, and then using the percentage to find the mass of the solute, converting it to moles, that tells me how many moles I had per 1 liter.
You have to show work on the C or to get credit on the C test.
Yeah, you would. You should.
You just do 12, like 11.9 divided by 1.
Yep. Go ahead.
Hypothetically, if it had been 2 liters, would you had it divided by 2, or would the process above have already given you the correct moles?
Yeah, it would have taken care of itself.
Okay.
Pretty sure.
Uh,
You can really, to be honest, you can choose whatever volume you want. And like you might have to do a little bit of finagling on the math, but you can figure it out. Okay. Not awful. Let's talk about how this problem incorporates the rest of everything else. By the way, this is how I buy it. And When you buy hydrochloric acid, it comes as 12 molar. So like we're really close. The density's whatever. What's that? That's that's just how that's the number they chose, I guess. I don't know why.
That's a good
But,
number. I like it.
all right. So there's more.
Even, not odd.
What's that?
Odd numbers mean that.
Oh, wow. I was born on 2 odd numbers, 3 odd numbers,
I was born
2
on an odd
primes.
number.
Okay, here we go. Here's where this gets trickier. Not trickier, but it incorporates other chapters. Give the net ionic equation if solid calcium carbonate was added to this solution. Could you do that? Well, what's the solution? It's hydrochloric acid. Do I care about the water? No, it's in a solution. So what am I putting in it? Good job. CaCO3. I should always double check my charges. +2, -2. So that's good to go. Then my arrow. What's it going to react and form? All right, genius over here. Water. Carbon dioxide. How did you remember that?
The CO3.
Okay, the red flag right here from forever ago. We had when an acid reacts with the carbonate, it makes water, carbon dioxide, but I'm not done yet.
And then your salt.
All right, my salt, which is CaCl2. Then there's still lots to go here. Is CaCl2 soluble? It is AQ. It's okay. Chlorine is always soluble except for with silver, lead, mercury, and gold, if I remember right. So it's with calcium, so it's aqueous. Okay, so the other thing you need to know is a hydrochloric acid a strong or a weak acid? Strong. So that means this is AQ, and then this says solid. Okay, is this the answer? No. What do I need to do? All right, I need a 2 in front of the HCl. Is that the answer? No. I think that did balance it. It did.
Never mind. Yeah.
What am I missing? I need the net ionic. Man, I love this because it's such a huge review. Hey, don't you do that to me. Think this through. Anything that's in the aqueous on both sides is gone, right? So what's the, all right, so Cl is definitely out of the equation. Is anything else eliminated? No, it's not. So you would say, and remember, you got to carry this, 2H plus CaCO3 solid. So this was not eliminated because it was aqueous on one side, solid on the other, right? Goes to H2O liquid. So the H wasn't eliminated because it was aqueous, but it was part of a liquid on the other. Plus CO2 is a gas. So it was not, nothing in that was eliminated. Plus Ca plus 2. You can put aqueous on these, but by putting a plus and a plus, it doesn't matter. Yeah. That's a long time ago, but does it jive? You remember sort of that idea? Lots of stuff. This question, I love it. I wrote it, so I'm biased, but
I remember the first of the trimester when that seemed hard.
yeah.
Really, I got.
Or not the first of the trimester, the first of the year.
Yeah, I got Net Ionic, and then everything after that slowly went. I remember the red flags too.
The red flags are CO3, S minus 2, and SO3 minus 2. Those are your 3. These 2 both break down into water and then carbon dioxide or sulfur dioxide. This makes hydrogen sulfide
And
gas.
they have to be with acid.
They need to start with an acid, yes. Well,
It has to
It has to react with an acid, sorry.
Yeah, that's for reaction.
The order doesn't matter.
The Stephanie left.
Okay, now let's look at E. I'm not going to do E all the way through here. So we're using this equation essentially. If 28 grams of it reacted with 200 milliliters of the above solution, how many liters of CO2 would be created? The pressure is 1 atm, 300 K. Ignore the vapor pressure of water. So what equation do I have to use for E? Pivner. All right, so you have to have this problem up here done to figure out the volume times the concentration. The concentration was the answer to one of those up there. Then you just Pivnered it like we did all of last chapter, like chapter 10. It's a doozy. Bonus, I haven't had this on there for a few years, but we'll learn about the boiling point and elevation, or sorry, constant today. I love watching Caitlin panic. And then she gets 100 on her test. Did you say lies? Whatever. Oh, well, I said that and you just put your pen down and went like this. That, yeah, sorry. All right. This question, you will have this question on your test. All right. Everything changes, but it's the same question. Now, if you go to, do I have one open here? I don't. If you go to the practice problem page in Canvas, you can practice that test problem over and over. If I remember right. I hope I do. Oh, I finally put the chapter 11 vocab in. I forgot until today. If you got a perfect score, then you got a perfect score. If you didn't, you have another chance to repeat it whenever you feel like it. So if you go to, maybe it's in chapter 11. So it's in chapter 11 through 13, free response test help. Look at that. Oh, I better change that because we have that same problem. Well, no, we don't, because we did 40 and a different number, and we did a different number in 1.28, so we should be fine. Then you can try on your own, and remember, you can go to the spreadsheet, you put in the numbers you made up, and you can see those answers. So someone's been here before. All right, you put in the numbers you chose, and it will give you what the answers are, if you remember. Okay. Yep. Well, you do it, then you check your work by checking the formula. On the problem we just did, it was 28. So it's pretty much this same problem. But yeah, we had 0.09, so it is different enough. Okay. Anyway, you can practice those there. We're definitely not on track to test tomorrow. I know that breaks your heart. Oh, never mind. I thought you guys would be mad.
I was so mad, Dave.
I knew Fabian would be livid.
I would be.
Please.
There's been so many people that these guys wish was only on the test that I'm sure they're so ready for it.
Everybody's so ready. Okay, here we go. The last piece of the chapter 11-13 puzzle is colligative properties. Colligative properties. We've applied these in your life, like just this weekend. Colligative properties are the reasons that we put salt on the roads. It's the reason why Willard Bay freezes, but the Great Salt Lake does not. It's the same thing. Uh-oh, there's my audio back. When we go to make ice cream, we put the salt on the ice so that the solution surrounding. I got to figure out what's going on with this thing once in a while. Anyway, so the solution that surrounds the ice cream tube is colder than it really should be. Anyway, colligative properties.
Yeah, because it drops it.
Right.
Can go tell all the temperatures on it.
Right. So this is so annoying. I don't get it. So our tube of ice cream, we would have ice surrounding it, and if that was it, it'd be fine, but it wouldn't get as cold. But if we add salt, what happens as some of this naturally melts, we can have the liquid that's like 100% contacting the surface area here. And the liquid that is surrounding this is below freezing, which means that we can make something in here get below freezing. So that's how we do that. If we were not able to do that, it would take a lot longer time to make the ice cream. So one time I wanted to make uh, my drinks really cold, really fast. So I did the same thing in my cooler. I just poured in a ton of salt and dropped my warm drinks in, and they were cold pretty fast. I mean, not like 30 seconds, but like 10 minutes instead of an hour. Yeah. Okay. Changes in colligative properties depend only on the number of solute particles present, not the identity of the solute particles. This is typically questioned at the end of a long free response about colligative properties. And it says, well, what if we used, calcium chloride instead of magnesium chloride? And you'd say, it wouldn't matter unless the concentration changed. All right, colligative properties that we are going to talk about are vapor pressure, boiling point, and melting point. Osmotic pressure is not really in AP. So, I mean, we'll mention it, but that's about it. So, what you need to know for sure are that a colligative property is that vapor pressure is lowered. The boiling point is elevated. And those two are definitely tied to each other, by the way. And the melting point is depressed.
Aren't they inverses of each other? Well, no, they're indirectly related or inversely related.
Yes.
Where one goes up and the other one goes down.
Mm-hmm. All right. Do we have that? I'm moving on. So, because of solute solvent intermolecular attraction, higher concentrations of non volatile solutes make it harder for solvent to escape the vapor pressure. So, if you think this through, it will sort of make sense. A vapor pressure is when a water molecule or solvent particle leaves the liquid. But if there's some attraction now between this particle and this particle, then it's less likely to leave because there's a force of attraction holding it into the liquid.
Which doesn't that slow the particles down when there is attraction?
It doesn't necessarily slow them down because it doesn't like directly change the temperature, but it means if I add energy or take away energy, there will be an effect. Okay.
What is solutes that would increase the vapor pressure?
I don't know, probably, but not generally for sure. I'd have to think about that one. Okay, so make sure you understand and could explain this. So, like the ID means ion dipole. So, if this were salt and water, the salt particle and the water particle would have some attraction. In order for the water particle to evaporate or turn to a vapor, that has to be broken. So it means that there's less vapor on top than there should be if we add a solute.
We're adding more intermolecular forces.
Yep. And that causes a lower vapor pressure. Now, if we think about this same thing, it'll come up in a second. If we're saying that less of it escapes, we could also say it takes more energy to make it escape. Does that sort of make sense?
This would be the reason why it has a higher boiling
which would be the reason why it has a higher boiling point. Any anytime anytime we cause the liquid to be more attracted to itself, we raise the boiling point. It takes more energy to break the attractions. All right. So yada yada, same thing I just said. Therefore, the vapor pressure of a solution is lower than that of the pure solvent. If you learn nothing else, at least memorize this part. This could give you like 3 out of 5 on a question. How'd the pictures go, Coop?
They were good.
All right.
I mean, hopefully.
Yeah, hopefully.
Guess we'll see.
I was in one. I tried to suck in the best I could.
My problem is I don't open my eyes all the way when I smile sometimes.
Mm,
But we'll see.
okay. All right. So if we add a solute, the vapor pressure decreases once again because of the attraction between the solute and solvent. Now, as every single thing we've ever had in chemistry, there's math. Yes. All right. Ethan, you got it? Okay. Raoult's law. This is the math. It's not as hard as it looks, especially since we already know how to find x of a. All right, so Raoult's law says we have our pressure of A, or our vapor pressure, is equal to this mole ratio of A times the pressure naught. This would be what it should be. Yeah. All right, so this is what it should be. This is what it will actually be based on this. All right, now this is really important right here. So we'll get there, but that is definitely really important. You know, XA is the mole fraction of compound A. All right, P naught of A is the normal pressure, vapor pressure of A at that temperature. So this is really, really important. This is one of those times when you want to make sure you have the vapor pressure of the solvent.
So this is when we're doing molality.
This is where molality will be involved. It's coming up, yeah. Okay, now, the reason why we want the vapor pressure of the solvent is because if I think about it, salt, like solid salt that's going to dissolve, it doesn't really even have a vapor pressure. It's a solid at room temperature. So we're talking about changing the boiling point of the solvent. So we make sure you do this math with the solvent.
Putting salt in your water makes the boiling point less.
It makes it higher. Yep. Now, some people have asked in the past, they're like, oh, that's why you put salt in your water at home to cook faster. And that's not true. The amount of salt you have to put in to make an appreciable change is way more than you would be able to taste or like stand eating. You'd need like a half a cup of salt for your mac and cheese. And no one's doing that. I don't care how addicted to salt you are. That'd be disgusting. All right.
Guys, I'm
So
cooking. Want some?
we'll do a practice problem on this tomorrow. I don't even know where I wrote this part, but oh, I guess it's right here. But we'll talk about it tomorrow. Cooper, you weren't here. The test is not tomorrow. But here we go.
What is P of A?
P of A is right here.
What are we finding?
We're finding the new vapor pressure.
So this would be the vapor pressure of the solution. So solute and adding salt.
Yeah.
Yep, this is the new vapor pressure.
I don't think it's Friday.
Well, it's definitely not next week. I'm hoping it's Thursday. Every day there's just a new reason I push it back. All right. maybe the test. Okay, here we go. So non-volatile solute-solvent interactions also cause solutions to have higher boiling points and lower freezing points than pure solvents. All right, what I mean by non-volatile is things that don't evaporate. Like they're not, so like if I poured ethanol into water, the ethanol would just float on top and evaporate quick. It wouldn't really mix in the first place. And so we're not really talking about that. We're talking like putting an ionic salt in. All right, now another way to say this is the following. The solution stays a liquid over a greater temperature range than the solvent because it boils higher and it freezes lower. You with me? If it boils higher, like let's say in water, it boils at 102 and it freezes at 22, my range is 80 versus 32 and 100, where my range was 68.
Is it because it's harder to break apart the attractions between the salt and the water?
That's for the boiling point. That's why it's elevated.
And then it's decreased because there are more attractions.
The depression's a little bit more complicated, and it's the next slide. No, it's not. What's that? I know. Okay, so there is a slide somewhere with Y. It's right here. Nope. Okay, there is no explanation, but I will tell you. I swear there is one, but I must have deleted it somewhere. All right, so depression. We all know where that comes from. When
Not one of
something,
these classes again.
yeah,
The home squad already came.
when something freezes, everything locks into place, right?
Yeah.
If I add a solute, things get in the way of these bonds. And so when you want to go, that diamond sucked, but when you go to lock everything in, since there are things now between the pure solvent,
It's harder to
you have to get it colder and colder before they find each other and lock in.
So like what we talked about with the salt water and why we put salt down.
Right. This is exactly why we put salt down.
Because it will lower it lowers the freezing
It,
point.
it interferes with the crystals being formed. So if they're independent, we call it a liquid. If it's a crystal, we call it ice.
Does it get in between them because it's
It really wasn't that bad.
molecules then?
Yeah.
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 The attractions between
Yep.